Hey guys. Okay. So as I mentioned, next week. So this week is a regular week. We said then on Thursday we'll have an extra hour, so we'll have until 7. Next week we will not have lectures. Well, Tuesday not supposed to be even a lecture because it's election day, and Thursday I will not be around, so there will be no lectures next week. No lectures. As you've seen, I put the last problem set on Sunday. That was because I had some technical issues with the system. Was supposed to be on Friday, so we have 1 week. I'll put the next problem set this Thursday. Okay, so let's not waste time because we don't really have that much time left in the semester, and there are plenty of things to do. So we're speaking about the Dirac equation. Let's do a recap on what we did. We said that the main motivation was to find a first order equation which will give us non-negative probabilities and consistent with Einstein's relation. And Dirac suggested an equation which looked something like I motivation first order non-negative probability energy and consistent with p squared is equal to p squared plus times. And Dirac suggested an equation which looks something like I dt psi is equal to minus I alpha j dj plus beta m psi. And we find that there are certain relations that these alphas and beta, alpha j's and beta, has to fulfill, which means that alpha j and beta are cannot be numbers. Matrices. And the minimum matrices has to be a 4x4 or higher. And I mentioned that if there is no beta, if it's a mass less, then we can do with the 2x2 matrices. That's called a way of spinors. And then there was an issue which made a little bit of confusion. So I wrote down the Hamiltonian here. Right, this is the Hamiltonian operator as alpha times p. P is an operator. But now we have 3 of these, so I put it in arrows here, right? So alpha, these are components, that coefficients that multiply the p, but they are matrices by themselves. Plus beta n. And then we said that this operator operates on a 4 vector, which is known as the Dirac spinor, which has to have a component, 4 components, psi 1, psi 2, psi 3, and psi 4. And I mentioned that these coefficients, they cannot be numbers, they have to be matrices, and there are several representations. I showed you one. In the homework, you're supposed to work a slightly different one. And one of them is called the Dirac pod representation. Where beta is I 0, 0, minus I. These are all 2x2. And alpha I is a 0, sigma I, 0. And these are poly sigma matrices. The same one that you've seen in quantum mechanics. And we show that this actually solves the probability, negative probability, by defining that rho is psi dagger psi, and J, the current, probability current, is psi dagger alpha psi. Again, these are 4x4 metrics. And then we looked at the spin of the Dirac particle, and again, spin is something which is intrinsic.
In the Dirac matrices, don't you need one of them to have a star?
No.
But then it's not Hermitian. I want it to be Hermitian. Okay, sorry.
No, that's fine. There's no problem here. And then we looked at the commutation relation of the Hamiltonian. So to calculate the spin, we started by looking at the commutation relation of the Hamiltonian with the angular momentum, external angular momentum, hd. Yeah. Now, of course, L is R cross P, right? And so we can treat these as the coefficients of the P. Right? So I don't need, so obviously they will commute with anything because it's just the P commuting with R cross P. So these are just coefficients which I can take out of the calculation. And we added up, this is equal to I minus I alpha, the coefficient, cross. When I say cross, because it's alpha x py minus alpha y pz, etc. Right? So it's not the same coefficient. This is just a shorthand of notation. And then I said, okay, but how can it be for free particle? So this is a free particle. So that means that there is an external or additional angular momentum component which is intrinsic to the particle. We show that by defining the sigma matrices. So I said there is an additional component or angular momentum component, which we call Sj operator, which is half sigma j. These are matrices, sigma j. There's no summation. This is just a sigma, which is defined as 1/2. And again, sigma j, 0, 0, sigma j. This is intrinsic. And since this is intrinsic, this would commute with the alphas, not with the p, which is extrinsic, external. Then we calculate what is the commutation relation of hd and sigma. Sorry, S. Well, it's just a 1/2 here. And we show that this is exactly what we have here with the plus I alpha plus p. So we conclude that hd commuting with j, which is L plus S, is conserved. So the total angular momentum is conserved, extrinsic plus external plus intrinsic. Which means that inherently the Dirac-Spinor has a spin, and we show that the eigenvalues of this spin would have to be 1/2. This eigenvalue plus minus 1/2. So intrinsically, Dirac equation, without even, I don't know if he was planning that, I guess not, but you know, to test the legend, right? Ended up that this equation describes inherently a spin half particle. Then we said we can take this equation and write it in a covariant form. Covariant form means a form that does not change when we make a Lorentz transformation. So two different observers write down the same equation. We said that we can by defining the gamma matrices, gamma 0, which is beta, and gamma I is beta alpha I. The Dirac equation gets the form I gamma mu d mu minus m psi is equal to 0. And these gamma matrices apparently have some very interesting properties. So about computation relations, they fulfill. It's called a Clifford algebra, and you are supposed to practice that a little bit at home. All right. And we showed what they look like in the Dirac, Pauli Dirac representation. Of course, in different representations they look differently, but their general properties remain the same. Okay, and we proved that the Dirac equation is covariant. I'm not going to repeat the proof. And we wrote down the covariant form of the current and the probability density, right? So J mu, we wrote it as rho J is equal to psi dagger gamma 0 gamma mu psi. Or psi dagger gamma 0, this is called psi, this is denoted as psi bar gamma mu psi. After doing all that, we looked at the solution, and we started with a solution for particle in rest. And we search for a solution of a plane wave solution of the form psi is equal u e 0 e minus I e t. It's at rest, so p j's are 0. And we find that there is a quite simple solutions, right, which would be the u 1 1 0 0 0, u2 is a 0 1 0 0, u3 is a 0 0 1 0, and u4 is a 0 0 0 1. So quite simple solution. And then we realize that these two have positive spin, namely if I operate with S Z on the U1 as Z U1, we end up with half U1. So these are also eigenvalues of the spin with spin up. And of course, on U2 it will be a minus, and U3 plus, and U4 U3, and as in U2 or U4 is a minus 1/2 U2. I think this is as far as we managed to go last time. Again, since we don't have time, but we have plenty of interesting stuff, I want to speed up things as much as possible without loss of understanding, without losing your ability to trace what we do. I will put my lecture notes, I keep on updating them. I'll try to do it as soon as I can. Questions? No? Everything is clear? Yes.
Just to be sure, I'm the commutation of the Hamiltonian with the spin says alpha cross p.
Yes.
And so if p is 0, the spin is not changing.
If p is an operator here.
Yeah.
But yeah.
If the particle is in rest,
Yes.
And if the particle is moving, then the spin is changing all the time.
Correct. That's it's kind of strange, but yes, it is.
And it's not changing in magnitude, it's changing in direction. Because
in principle, yes, that simply means that this would not be an eigenstates of the. So you know that when you make a measurement, you see one of the eigenstates, but that means that the particle will not be. This will not be a good solution for the particle. But this says this is a solution for a particle at rest. And you're absolutely right that when the particle is not at rest, that is not going to present a solution. So the spin will change, yes. In fact, that's what we're going to do right now. Yeah?
But also, I think eventually the spin will be connected to the magnetic moment, maybe?
Of course.
So if you just drive an electron in the magnetic moment, it should sort of fluctuate?
Yes.
Okay.
Yes.
How does it make sense with Stern-Gerlach experiment?
When you make a Stern-Gerlach experiment, you make a measurement. So it must be in one of the eigenstates. And here you're not making a measurement. I'm just saying, okay, look, these are the eigenvalues. Okay. Now let's see what happens. Let's wait with this question 5 minutes and then we'll get. Okay. More questions before I move on? No. So the next thing is, which is quite straightforward, it's what we did so far, is to look for a solution for particle which is not at rest. So let's do that. So free particle solution, or general free particle solution. So the general equation we had for a plane wave solution would now read gamma mu E mu minus m u is equal to 0. Right. Before we only had gamma 0 p0, which is E, minus mu is equal to 0. Right. Now we had, when we wrote down this solution, now we have this equation. General solution, general equation. So let's just expand that. And again, the 2 by 2 notation. So gamma 0 is I 0 0 I. Sorry, minus I. Right. E. And then gamma j pj would give us a minus 0 sigma dot p minus sigma dot p 0 minus m I, so minus I 0 0 I m u is equal to 0. Again, each of these is a 2 by 2 matrix by itself. 0 0 0 0. And the sigma dot p, which we derived earlier, you can write as pz and then px minus I py, px plus I py, and minus pz. Just by substituting the Pauli matrices. So again, if I expand U in terms of 2 spinors, so U would be UA, UV. Again, each of these is a 2 spinor. Then, and collect terms here, then I get E minus m I. Here it will be a minus sigma dot p. Here I have a sigma dot p, and here it will be a minus E plus m I. UA UB is equal to 0. Yeah.
How do we move sigma is a 2x2 matrix?
These are probably sigma matrices.
But P is a 2 vector. So how do you multiply it? Or
You have three matrices like that.
But how do you
Sigma x, sigma y, and sigma z.
actually, so you multiply the sigma x by px and then add them all, okay.
Right.
Sure.
Sigma x px plus sigma y py plus
And
sigma z.
and px is a scalar, not a vector.
Yeah.
Okay.
Okay. Just a short notation. That's all. And these are 2x2 matrices. This is px, py, pz. This is just a short notation. That's all. Nothing to get alarmed about. So if you write these, you get a coupled equations for UA and UB, which will be UA is a sigma dot p over E minus m UB, and the UB is a sigma dot p over E plus m UA. Just by substituting. So we have a total of 4 solutions here, right? And up to normalization, we can simply start by selecting the 2 simplest possibilities, which will be right. We select UA, so select UA is a 1, 0, and the UA is a 0, 1. And then the UB will be automatically, right? These are 2 spinors, right? So 1, 2, 3, 4. This pen here, a very short half-life. So using these 2, I can automatically get the UB from there, and immediate results up to normalization, which I'm skipping for now because I'm lazy. So U1 of E and P is a 1, 0, and then we get the P as Z over E plus M, and the PX plus I Py over E minus M. Sorry, E plus M. But you can do the simple algebra. And U2 will be a 0, 1 Px minus I Py E plus M over P minus Pz over E plus M. Then for the other 2 solutions, we can simply select UB to be equal to 1, 0 and the 0, 1, and plug it in here. And we get the U3 and U4. U3 of E and P is.
Why you can just select?
Just a second, let me finish writing the result. It will be a Pz over E minus M, and then Px plus I Py over E minus M, and then a 1 and a 0, and a U4 is Px minus I Py over E minus M minus Pz over E minus M, and then a 0 and 1. So all these, after normalization, all these would solve the Dirac equation. plane wave solution with a general momentum, and of course that means that they will automatically satisfy E squared plus B squared is equal to B squared plus M squared automatically. Satisfy. Of course, in the limit when p goes to 0, what do we get back?
Of
course. We get back these guys. Right, as we should.
So don't we have the problem that E minus M going to 0? So and when P is going to 0, so you're dividing with 0 and stuff?
No, why?
Because
yeah, that can be.
No, that
it would be a problem. It can have to be a problem.
That may be a problem, but I guess if you take the limit properly, it will end up not being a problem at the end. But there is a different problem. What is the energy?
So why you can just select UA to be 1, 0 and 0, 1?
Just the simplest possible solution. You can select anything you want. These are simple ones.
Okay, that
you
they
chose
can-
those two selections and found
it
the
satisfies one of the equations. How do you know it will satisfy the other one?
I plug it in. That's how I constructed the full Dirac spinor. By
But
construction.
both of the equation need to be satisfied.
Oh, yeah.
right? So
Plug it
when
in.
you're
Just
choosing-
plug it in. I chose a
Okay.
1, 0. Just plug it in and set up to normalization. I did not care about normalization.
You also
Select.
need to
Yeah,
use-
do it, and you see it. Just do it at home. I don't have time to go over every step here, but it's quite obvious, right? I select that, I plug it into this equation, I get it. How do I know that this will be satisfied as well? It will.
And you need to use E squared equal to B squared plus M squared.
Yes. That's it. This is automatic.
Yeah.
This will get automatically satisfied. Okay. But there is another issue, right? If I look at the U1 and U2 solutions, you'll find out that the energy E for U1 and U2, you get the E is equal to plus square root of P squared plus M squared. And for U3 and U4,
Couple and minus.
we get that E is equal to minus square root of P squared plus M squared.
Actually, this solves the 0 problem because if E is minus, then in the denominator E minus M was.
Yeah, possibly, yes. Then this will give you a plus, so that there's no issue. Possibly. I mean, play with that. I didn't have time to look at that.
If E is negative,
No, that's fine. I'm just not worried about it. So we did not get rid of the negative energy. There are 4 solutions. 2 of them have positive energy, U1 and U2. We have 2 solutions with negative energy. Okay. So, about the maths, I mean, if you have problems about the algebra, I assume you know how to do the algebra. Check it out, there's no real issue. Let's talk about the physics. So what did Dirac do? We derived an equation. Hey guys, questions from or discussions from it. If you are really concerned about the algebra, you simply have to do it at home. We don't really have the time to go over each of the derivative of this. Just plug it in, do it, and fine. If you want, if you really insist, I will give it to you as a homework, so you'll have to do it. Actually, you want to do it, otherwise I'll give you more difficult questions and then just do some simple algebra. That's something that I always learn. People know how to do the algebra. I mean, I could have a typos here. It's unlikely because I checked myself, but it can always be. I'm not saying. But normally, you know, when people have difficulties, it's not in the algebra. The difficulty is understanding. Understanding the physical scenario, not to do the math. Doing algebra, you know, if you can do it yourself, ask the computer, it will do it for you. Understanding is a difficult one. What do we have here? So Dirac looked for a solution. He found a solution. It's a great solution. He even predicted that all these particles must have a spin 1/2. Amazing. And then he got a solution. With this solution, there's an inherently negative energy states. Now, what's the interpretation? You cannot simply, in quantum mechanics, you cannot say, okay, I'm just ignoring that part. I don't like this part, it's unphysical. But it is part of your space. Right? It's part of the space of solutions that you find. So you must give it some interpretation. And what was the interpretation? Of course, if there is negative energy solutions, why would not the particle simply lose its energy and go down to minus, minus, minus until infinity? What was Dirac's interpretation? And you understand the problem. We have an electron, it has some energy, but we said it is in a state. Let's say it's in a state U1 or psi1. Right? It has some energy. Right? But there are available states for these electrons which have a lower energy. So why wouldn't the electron simply decay into these lower energy states sooner or later? What? Yes, but when Dirac wrote the equation, there was no antiparticles, no.
Again, what is
the question?
The problem is the following. E equal to 0. Right? There are allowed solutions. There are allowed energy levels of Dirac electrons. Right? But there are also negative energy solutions. What prevents the electron, which is in this energy, to emit a photon or do something and go down to a lower level, and then to an even lower level, lower. Why wouldn't it do it?
Yeah, maybe there is a problem with the E equals to 0.
No. Yeah.
I think I remember something from quantum mechanics that in the ground states, if you're trying to operate.
But we don't have a ground state.
Yeah, but there is no ground state here. Okay. It's true in quantum mechanics, right? There is a minimum ground state, of course, but here there is no minimum ground state. Right? There are negative energies, and these negative energies would go to infinity.
אולי זה מה שאמרנו עם ים של החלקיקים שהוא חושב שהיה,
Right.
כאילו שזה מלא.
Right, exactly. So what he says is, okay, we have these states, but these states are filled with particles already. That's called the Dirac sea. The Dirac sea. And since these are fermions, right, they obey the exclusion principle, so you cannot have a situation where you have two particles in the same state, two identical particles in the same state. Right? So all the available states are already occupied. It's a little bit like a Fermi sphere. Right?
Can you ionize one of the particles from?
Yes. Okay. You can take these and raise it here. Then you get a hole. And you'll see another particle. Yeah, you can.
They did it in the lab.
Wow. And
The more specific question.
no, what
Did
will
we observe the
what
negative
we'll call
energy?
that? This is exactly what will be the antiparticle. When you make when you're removing the particle from here, right? Then you get a hole in the sea. Right? What will be the charge of this hole? have to be
minus
positive, right? If the electron has a negative charge, they have to be a positive because now you're excluded a particle from the sea of particles, right? And this hole will start to behave the same way as the electrons. Right? So this was Dirac's idea, and which essentially said, okay, we don't see them because they're all occupied. So E equals 0 is equal to a Fermi sphere, or a Fermi level. Yes, you can take away particles, leave the holes. These holes will act like these are the anti-particles. Now, we know this picture is incorrect because we know they're also anti-bosons. Right? So they do not obey the Dirac equation. But the idea is quite nice. Yeah.
Didn't we just from the beginning derive the Dirac equation because the Klein-Gordon equation was problematic because of negative energy?
Yeah.
So why couldn't you just say that at the start?
Because I said that the main problem with Klein-Gordon was not so much the energy, it was the negative probability. And Dirac solved this problem. There is no negative probability in Dirac's equation. And probability is always positive. The particle is there somewhere. But yeah, Dirac was unable to solve. He got a great achievement, but he was unable to solve the negative energy problem. So he had to think of some interpretation. But since he got these were fermions, then they obey the Pauli exclusion principle, so it actually fit quite nicely with all the physics that was known at that time. Questions more? Okay, now let's look a little bit at these anti-particle spinors. Let's do it in a more modern way, the way we think of these anti-particles. Particles, spinors. So we could continue on to work with these U3 and U4, which will give us these negative energies, but we don't like negative energies. They're pretty confusing. So instead, we're going to work with antiparticles, spinors, which will have positive energy and positive momentum. So for antiparticles, rather than particles with negative energy momentum, we work with antiparticles with positive E, namely that E is plus P squared M squared. So instead of the U3 and U4, we'll move to V1 and V2 by reversing the signs of E and P. So we'll define the anti-particle spinors. V1 of E and P will be a U4 of minus E and minus P, and V2 of E and P will be U3 of minus E and minus P. And since we said that the U's should fulfill the Dirac equation, so U's, U3 and U4, obey the Dirac equation, which we wrote as gamma mu P mu minus M U equal to 0, then simply put a direct substitution with a minus e and a minus 3, and you get that, and you end up that the v spinors fulfill Dirac equation with a plus here. Gamma mu p mu plus m v is equal to 0.
But why don't you add a minus in the p?
Yeah, you do add a minus in the p, and then you just remove the minus because it's a 0, and then you end up with
Ah.
something.
I meant.
Okay? So the viz should obey this equation. And then we simply need to repeat exactly the same steps as deriving the Dirac spinors, basically simply replacing m with a minus m. So replace m with a minus m, and then you get that v1 e and p is ex minus I py over e plus m, and then minus pz over e plus m, and then 0, 1, and v2 of e and p is equal to pz over e plus m, and then px plus I py over e plus m, and then the 1 and the 0. And of course now e is a positive square root of p squared plus m squared. And of course the full solution of the Dirac equation, well, it's the inverse Dirac equation, so we'll just write down the top psi, put a c here, should be a v, I think. Let's say c of 1, 2, full solution is of x and t is v 1, 2, e and p, e to the plus I p mu x mu. So far, nothing should be alarming.
So,
Yeah.
what is written on the left-hand side? Psi, is it a C? What is
Yeah, I
that?
put the C here to because it's a Hermitian conjugate.
And the 1 and 2 mean that it's two solutions, right?
Yeah, there are two solutions here, right? 1 and 2. So total we have 4 solutions for the Dirac equation. 2 of them represent particles, 2 of them represent antiparticles. And each of these 2, one will have a spin up, one will spin down. Same for the antiparticles. What about the operators of the antiparticles?
What have you done with the mass? You replaced it with the minus sign?
Said, I want to solve this equation. I know a solution of this equation. So the solution to this equation is exactly identical if I turn m into a minus m.
Okay.
That's all. And I just wrote it down. I didn't even have to do any calculation.
Okay.
So does that mean that antiparticles have a negative mass?
Negative energy. Have a positive mass but a negative energy.
Wait, but so
We-
how annihilation works?
What?
How annihilation works? Because you generate energy.
Again, they have negative energy and negative momentum. So you can view them as particles going backward in time. Remember that we spoke about Feynman's way of looking at them. It says, okay, so we have particles going backward in time is like antiparticles going forward in time. So when you switch the time back, you gain again the mass. Okay? So the treatment of antiparticles is the same as particles, but everything else, all the intrinsic properties, would be reversed. Okay, I guess it takes more than just me saying that. You actually have to go and read it properly to digest it a little bit. Okay, now let's look at the operators on the antiparticle spinors. Operators and antiparticle spinors. Right. So you know the wave functions have this extra sign here. E to the I. V times e to the power I p mu x. So because of this e to the I p mu x mu, I cannot use the standard quantum mechanical operators because I'm not going to get any physical thing. So if we try h psi is I dt psi, because we have the plus sign here, we're going to get a negative with a minus e psi. It's not particularly useful. And similarly, p psi is going to give us a minus p vector psi. This is operators, right? The hat that I'm giving it. So, in order to get the correct energy and momentum, we must redefine the operators. Right, so, redefine the operators. So, H operator, I put a V to denote that it works on the V spinors. Rather than I d over dt, I'd call it a minus I dt. And P operator, then V, would be a plus I. Blah, blah. And what will happen to the orbital angular momentum? Flip, right? So L, which is R cross P, would go into minus L. So what does it mean if we want to conserve the total angular momentum?
We need to subtract
H B L plus S is equal to 0. What does it mean about the sign of the spin?
also flip.
Has to flip, right? So that means that the sign of the spin of the antiparticle is exactly the opposite, right? So that means that S of a V is a minus S. If you want the, sorry, the vector. I need to operate it now. Now remember when we did the derivation of the spin of particles at rest, right? For particle at rest, we had S Z of U3 be equal to 0 was 1/2 U3 be equal to 0, and SZ of U4 be equal to 0 was a minus U4 of be equal to 0. Now we have that SV is the opposite of S, right? And we defined V1 to be U4 and V2 to be U3. So we have that V1 of P equal to 0 is actually U4. of p equal to 0. That means that what we get now? We get now a spin up, the opposite. And the same for V2, p equal to 0 is U3, that's p equal to 0, which is now spin down. Cool, isn't it? I just showed you that the spin flips between particles and antiparticles. And again, this is completely in line with this C interpretation that I gave you, right? So if I remove a particle from the C, it has a spin up, so I'm left with a spin down. Makes sense?
Just how you define the antiparticle, right?
Again, it's an interpretation, right? I said, okay, I have a solution to the equation. What does it mean physically? Solution.
When you are measuring antiparticles, so you will get spin down if the
in that specific
particle,
state, in this state, yes, it will have a spin down.
When you are measuring, measuring V.
Yeah, you're going to see that. I mean, one of the problem sets. I don't know if the next one or one of them. You'll see when you start to when you're going to see that. You had that in the last problem set, not the one given to you now, right? You have to have, in order for interactions to occur, right, angular momentum needs to be conserved between incoming particles and outgoing particles. Mm-hmm. So the same here, right? I have to have that the total angular momentum spins have to be conserved. So that will, when do you see that? When you're saying that some interactions between particles occur and some others do not occur, although all the other requirements needed are fulfilled. Okay. That's all. Okay. Right. P is equal to 0. This is P equal to 0. Huh? Because the S3 of U3 give us a spin up, and then I have to work on that with the opposite. The antiparticle gets an opposite sign. That's all. It will be true anywhere, any frame. Trust is one specific example. Okay. More? You happy? Okay, that's what you're going to here. Let's look at the parity operator. Parity operator. I said that the parity operator is quite central, right? Because in all the QED and QCD processes, so basically all the electromagnetic and strong interactions, it is conserved. It is not conserved in weak interactions. They violate. Now, let's look at the transition properties of the Dirac spinors under parity. We observed QED, QCD. QCD is quantum chromodynamics. It's a strong interactions. What are transformation properties of Dirac spinors under P?
It will not concern on the weak interaction.
No.
Why?
Why? It's a good question. Why? It violates it. So, under parity, so it's a vector. Under parity, r goes to r prime, which is equal to minus r, and t goes to t prime, which is t. Time is not changed under parity. Now, Dirac spinor, remember, Dirac is not a scalar, it has an intrinsic degrees of freedom. So what happens to the intrinsic degrees of freedom of a Dirac spinor under parity? That's the problem we're trying to solve now. Okay? So, suppose psi is a solution to Dirac equation. I gamma 0 dt plus I gamma j dj minus m psi is equal to 0. So let's say that we operate p on psi, and the result I'm going to call psi p. So psi p of r prime and t prime is p acting on psi.
Can you explain this last line you wrote? Psi p, it's
Psi p is the Dirac spinor. Now I'm acting on the system with the parity operator.
so psi p, it gets the reversed coordinates.
Now everything is in the reverse coordinates. Right? Again, there is external degrees of freedom, right? And location is something external to the particle. Right? It's there. Right? It's external. We define what is the location. And there are intrinsic degrees of freedom which are internal to the particles. Right? And there are all the information is inside psi. Right? So now I want to know what happens to this intrinsic degrees of freedom of psi under parity. Let's say I act on p on the system. Psi I know obeys this Dirac equation by definition. Now I'm operating on p. So the new wave function operates with p. Then I have the new Dirac equation in the new coordinates to be I gamma 0 dt prime plus I gamma j dj prime minus m psi p is equal to 0. What?
Isn't it gamma j prime dj prime?
No, gamma j are just matrices. They are constants. They're just numbers, remember? So numbers, they are objects, but they are equal to the coefficients. Okay, now, what happens if I take psi p and act on it again with the parity operator? I get back psi. What? Yeah, no, by definition. Otherwise, it's not. Otherwise, it's not a good parity operator. Otherwise, it's not a good spinor. It's pretty much by definition. So, p psi p is equal to psi. So, I take the Dirac equation and let me write it as I gamma 0 dt plus I gamma j dj minus m p psi p is equal to 0. Because this is psi. This and this are the same. Now I take this equation, I multiply by gamma 0 from the left. then I want to express the derivation in terms of the new coordinates. Everything clear? It started from the this is the right equation. This is the right equation in the new frame.
I wasn't sure about the sign.
About what?
About the sign, but it's okay.
About the what?
The sign that I wasn't sure about, but
Sign?
no, it's okay. It's okay.
I know it's okay. I'm not sure. I'm just not sure what you were not sure about. Okay, so I multiply by gamma 0, and I'm going to express that in terms of the new coordinates, r prime and t prime. So what we have is I gamma 0, dt and dt prime are the same. Now I have dj and dj prime are, there is an extra minus sign. So I have a minus I gamma 0, gamma j, dj prime. Minus m is a scalar, so I can reverse it, I can commute it with the gamma 0, so minus m gamma 0. P psi p is equal to 0.
I thought in the top equation there is a tag on the t and j.
No, I just copied the direct equation.
Okay.
The only thing I did, I wrote down the psi as parity of the psi p.
And then you put the...
Here I did two things. I multiply by gamma 0 from the left, and I express the derivative in terms of the shifted coordinates.
Gamma 0 squared should be the identity matrix.
Yes, of course.
Okay.
Now I'm using also the anti-commutation relation of gamma 0 and gamma j, right? So remember that gamma 0, gamma j is a minus gamma j, gamma 0. So I'm going to write this as I. I'm still staying with the gamma 0 squared. So gamma 0, dt prime, plus I gamma j, gamma 0, dj prime, minus m gamma 0, p psi p is equal to 0. Okay, so I have this equation, and I have this equation. These two equations should be identical. Right, so this and this should be identical. Right. So, in order for these two equations to be identical, what do we get?
Gamma 0 psi p equals to p psi.
Gamma 0,
Gamma 0
p.
psi p equals psi.
Yeah, but psi p is psi p. So that means that what? We end up that gamma 0 p is proportional to the unity. But we know that gamma 0 squared is identity. We know that p squared is the identity. So what are the two options that we have here? P is equal to, so P is equal to plus gamma 0, or P is equal to minus gamma 0. It's quite cool. Now it's a matter of convention, and the useful convention is to take this one, right?
Wait, why again? I agree with those things. You say proportional to
Identity.
yeah.
gamma 0 is small.
But gamma 0 squared is identity, P squared is identity.
הם
Right,
שתי
can
נשכות
be-
כזה סקלר, זה הכל.
Okay.
בגלל שזה בריבוע האמצע הזה.
Okay.
Nope. It's not enough to sit in the classroom to review this material at home. That's quite cool. So that means that what? Under parity. What's the conclusion? So under parity. What happens under parity? Psi goes to p psi, which is gamma 0 psi.
Wait, but gamma 0 is operator.
It's matrix.
Okay.
Again, P is the parity operator, right? And it operates on psi. Gives him something else, psi p. Right? Psi p is defined here. And psi p is also equal to gamma 0 psi. It's not that. It's not that. Okay. It's not that difficult, right? So, for example, if we look at the particle at rest, again, remember what we're trying to do here. What we are doing here is looking at the intrinsic properties of the Dirac spinor. Right, so remember that, for example, for a particle at rest, particle at rest, P u1 is gamma 0 u1, which is 1 0 0 0 0 0 0 1 0 0 0 0 minus 1 0 0 minus 1. And then u1 is the 1 0 0 0, so this just gives us. So we got P u2 is also u2, P v1 is a minus v1, P v2 is a minus v2. So from here, conclusion is that intrinsic parity of spin half particles of a spin half particle is the opposite to the intrinsic parity of spin half antiparticle. Which again, it's not really surprising. Just cool to show that right away.
Why is that not surprising? Because don't we want to expect symmetry between particles and antiparticles?
Again, the symmetry, you can think of it in terms of reversing in time. Right? Maybe Dirac's interpretation is the easiest to think of, right? You think of it as an antiparticle is being a hole in a sea. So like there is a knot. Everything here is filled with particles. Now you're removing one of these particles, so you have a hole. So all the properties will be exactly the missing parts of that of the electron. Right, here you have an electron, this is E equal to 0, this is an electron. Now you're removing an electron from here. So you have all the properties minus. Maybe that's the easiest way to think of it. Another way, again, is a Feynman interpretation. An antiparticle is a particle moving, propagating backward in time. So when you reverse, then everything is flips. Difference is this is intrinsic properties. And again, I just prove it to you on the board. Intrinsic parity of a spin half antiparticle is exactly the opposite of that of a particle.
So all the intrinsic כל התכונות הפנימיות הן מתהפכות או רק קראת הפרקל הזוגיות?
Hey, I'm show you everything, yeah? For example, now parity is a multiplicative operator. So if you have a meson, for example, that is composed of a particle plus antiparticle, right? What's the intrinsic parity of a meson? Right. Parity is a multiplicative operator. So, for example, mesons, it is an F bar, right? It's a particle and antiparticle, right? So the intrinsic parity of an F and F bar will be a -1. There will also be a -1 to the power L. Right? That's the parity of the spherical harmonics, the angular momentum in between them. Right? And it comes from the Y and M. It's a -1 to the power L plus 1. For example, pions, right, these are the ground state of UD, ground states of UD bar, right, or DU bar, etc. Right? So, since they are ground states, that means that L is equal to 0, and the intrinsic parity of the pions will always be negative. So P of the pion is always -1.
Yes. We have U1, U2, V1, V2, and we can have also superposition of U1, U2, and I guess this would be electron in spin some other direction.
Yeah, just not an eigenstate of
Can we have a superposition of U1 and V1?
In principle, yes. I'm not sure what it would mean in a sense. I have to think of this first. I'll try to think of that and come back to you on Thursday. Not something that jumps to my mind at the moment. Okay. Let's move on and not we're going very slow. Maybe I'm way optimistic about my ability. Again, the problem is that we have a short semester. And I don't even know if I'm allowed to add a lecture. I don't even know. Okay. Let's go talk about now helicity. No, I think it's quite cool stuff, isn't it? Something. See if I need to change it. Spin and helicity. Okay. So we've seen it for a particle at rest. Right. As Z is 1/2 sigma Z. So it's a 1/2 sigma Z 0 sigma Z, which is 1/2 1 0 0 minus 1. So let's spin up and spin down for particles. sorry, this is okay, so particles, and this is for particles at rest. So this is spin up, down for particles at rest. Now there was a question that was asked, what happens when the particle is not at rest?
Asaf, can you explain that last line you wrote on the board?
Spin up, they represent the spin up and down for particles, which are at rest.
The speed up operators, you mean?
Yeah, Sz of u, of psi, will give you 1/2 psi. Sz of u1 is 1/2 u1, right? Sz of u2 is minus 1/2 of u2. Yeah. Eigenstates of the states u1, u2, u3, and u4 with eigenvalues plus minus 1/2. Nothing to be worried about. But what happens when the particles are not at rest? So particles that are not at rest or not eigenstates of Sz. So assume, again, without loss of generality, well actually it is with loss of generality here. Assume that the particle is traveling in the plus z direction. So P is equal to Pz. So U1 of E P is equal to plus minus Pz is 1, 0 plus minus Pz over E plus M 0. Then U2 is 0, 1, 0, and then plus minus Pz over E plus M. And then V1 is 0 minus plus Pz over E plus M, 0, 1, and V2 is plus minus Pz over E plus M, 0, 1, 0. Which we derived, yes. תציב במשוואות, אלא אם כן יש לי שוטה איפה שם. We just, sorry, this should also be a minus plus. We just derive these equations, so just put P equal plus minus Pz and just put it there. So, in this specific example, the particles move in the plus minus Pz direction. Then we do have that Sz of U1 of E 0, 0 plus minus Pz is a plus of U1 E 0, 0 plus minus Pz. Right. Same for E2. Minus 1/2 U2 E 0, 0 plus minus Pz. Well, P is Pz. It's okay. And then we need the P. And for antiparticles, we have the physical spin SZV, which is minus SZ. That will give SZV of V1 E 0, 0 plus minus P is plus half of V1 E 0, 0 plus minus p. And for V2 it will be a minus SZ V2 V 0, 0 plus minus p minus 1/2 V2 V 0, 0 plus p. Which means that the U1 V1 represents spin up. And U2 V2 is spin down. But again, this is sort of arbitrary because we selected the direction of motion to be along the z direction.
So in this case they are.
In this case they are, but that's because they're moving in the z direction. Now what happens if they're not moving in the z direction? So we already introduced, instead of defining the states in terms of external coordinates, which is something arbitrary, there is an internal property, which is helicity, right? So it's okay, can I erase that? You're not right. Natural definition is the use of helicity H, which is the normalized particle spin along the direction of motion. H, remind you, is an S dot P divided by P. So for the Dirac particle, Dirac spinor, or Dirac spinor, we have that H is sigma dot P over 2 P. The 1/2, which is 1 over 2p, and it will be a sigma dot p 0, 0 sigma dot p. P, of course, is the momentum operator. Okay. Now, the spin operator does not commute with the Hamiltonian. Therefore, spin is not necessarily conserved. But the helicity does commute with the Hamiltonian. The helicity operator does commute. Yeah. Hamiltonian. Look, I'm just spending all the I have here. Okay. I hope so. It'll last for the next few minutes. So, H, D, and H is alpha dot P plus beta M H, and this is equal to 0 just by substitution, which means that helicity is conserved. So we do have Dirac spinors, which are simultaneous eigenstates of the Hamiltonian and of the helicity. Yeah.
Where do we see that where do we see this equality? Like where do we see why this equality holds?
Just which equality? That they commute, you mean?
Yes.
Plug it in. Just gave you what is the Dirac, the helicity operator, you know, alpha and p, or just write it with the gamma matrices and you see the thing.
Oh,
okay. Right. Right, now the eigenvalues of the helicity operator are always plus minus 1/2. And they have a names. So eigenvalues of H are plus minus 1/2. And they have names. These are called right-handed and left-handed. This is a right-handed. This is a left-handed. Helicity states. One thing about the helicity is that it is not a Lorentz invariant.
So two observers would not be in the helicity.
Yeah, not necessarily. One simple way of looking at it.
Because V could be zero.
One way of looking at it, if you have a massive particle and the particle is moving in this direction, right, then you can always go to a frame in which the particle is reversing the direction. And you're just moving faster than the particle. Right. You cannot do it for a massless particle, it travels at the speed of light, but for a massive particle, it always travels at the speed less than the speed of light. So there's always a frame in which it moves opposite. Which means that the helicity is not a Lorentz invariant quantity. Okay, now we will, not today, but on Thursday I'll show you the Lorentz invariant quantity, but another quantity which is Lorentz invariant, it's called chirality, which is related to the spin, to the helicity, but it's not exactly the same. They actually coincide for massless particles, which travel at the speed of light. Okay. Well, it's going to take more than 2 minutes. Or I can just skip that. There is a part where I show you what are the simultaneous eigenvalues of the free particle Dirac Hamiltonian and the helicity. So I'll just write it down. Simultaneous, since the helicity is commute with the Hamiltonian, then there are simultaneous eigenvalues. Simultaneous eigenvalues of the helicity and Hamiltonian. There is a derivative which will take 15 minutes, but it's mainly, I don't think there is too much of a physics here. It's more math, so you know what, I'm just going to skip that. It will be in my lecture notes, which I will put on the course's webpage once I manage to make sure that they are free of mistakes, that the ones that I can find. So just give you these simultaneous eigenvalues, eigenstates, sorry. So the final results would be something like, so these are, I'm just giving you the final result without doing the derivative, which will take another 10 minutes. And it's just mathematical in nature. Basically, you can just do it. It's not more difficult than everything we did so far. So these are what we call the U up.
So it's eigenstates?
These are the eigenstates of simultaneous eigenstates. states of the helicity and the Hamiltonian.
Just finding the eigenstates of sigma p and
Essentially, yeah. So we basically write down the p as in spherical coordinates. So this is the magnitude of p, and then have a sinus theta, cosine phi, sine theta, sine phi, and cosine theta. And then just plug everything in, and we get that u up is cosine theta over 2 e to the I phi sine theta over 2, then p over e plus m cosine theta over 2, and then a p over e plus m sine theta over 2 e I phi. Switching again pen because this isn't really working properly. So I'm just going to write down cosine theta over 2 is just a c, and sine theta over 2 is just an s. And so this is u up, and then we have a u down, which is minus s, and then e I phi c, and then p over e plus m s, and then a minus p over e plus m c, e I phi. And then the v's look pretty much the same. V up would be p over e plus m s minus p over e plus m e I phi c, and minus s e I phi c, and v minus v down is a p over e plus m c e over e plus m e I phi s c e I phi s. And these are the simultaneous eigenstates of both the helicity and Hamiltonian. So this basically answers your question about what happens to the particle when it does it evolve in time.
What is the second component of u down?
U down e I phi. Sorry for my bad writing because I'm spinning up. E I phi c, and c is cosine theta over 2. All right. As I said, so helicity is conserved because it commutes with the Hamiltonian. You can find eigenstates simultaneous of both the Hamiltonian and the helicity. What it is not a Lorentz invariant. Which means that if you're making a measurement, you're one of those eigenstates, they will stay like that. If an observer will see something else. All right, we are running a little bit out of time. I skipped the derivation is again it's
For initial condition of some combination, linear combination of u up and u down,
yeah.
so the helicity will conserve.
The same as you used from quantum mechanics, right?
Yeah.
If you start with
Yeah,
some combination, it's not an eigenstate.
Yeah.
Then it will not, but it will be some combination of both of them.
Yeah.
The same as you have from quantum mechanics, it's not different.
What are the eigenvalues for the Hamiltonian?
What are the eigenvalues of the Hamiltonian?
Of
This-
the corresponding eigenvalues for the eigenstates, but for the Hamiltonian operator, not the Arati operator. It's the same.
It should be the same.
They are commute, so you are supposed to have 4 of them.
Not 4. U up, down, V up, down. Okay. Yeah. All right. Okay. I'll put when I put my lecture notes online. I'll do it as soon as I have time to do that. Then you can simply go over the derivative. It's not more difficult than anything else. See you on Thursday. Thursday again. Remind me to have a 3-hour lecture.
שהיה לגבי השיעור